Welcome back to the General Relativity course. Today's lesson or video is the very final one before we start the next section, and the next section is called General Relativity or the Einstein field equations. What we're deriving today is the last and final ingredient that we need before we can proceed to formulate general relativity, and this is called the geodesic deviation equation. You can visualize this as follows. Imagine you are on the surface of the Earth, say on the equator, you and a friend, and you are both looking exactly towards the North Pole, and you are, say, a few kilometers apart. So if you look at each other, you can just about see each other, but you're now facing both the North Pole and you start walking. As you walk towards the North Pole from the equator, you will notice that you will get closer to each other. And when you reach the North Pole, you will actually be within touching distance, which means if you move along geodesics, which are the great circles on the surface of the Earth, for instance, or the surface of a sphere, then the distances between two geodesics, two nearby geodesics, is decreasing. The geodesic deviation equation tries to make this more formal, and we will try to derive an equation that tells us the behavior of two nearby geodesics. We begin with a surface xa parameterized by two parameters lambda and s. Recall that when s is a constant value, we are writing here xa of lambda, so this is a curve. If lambda is a constant, then xa of s is also a curve, which means we have families of curves that are parameterized by one parameter, but if we keep them both arbitrary, we get something like a two-dimensional sheet, which we call a surface. So this can be formulated in n dimensions, for instance. And we assume that for fixed s, in this case we call this s0 to indicate that this is a fixed value, the curves, these are now curves because they only depend on one parameter, the other one being fixed. We assume that these are geodesics. With affine parameter lambda, which is precisely the situation that we had when I started the lecture on the surface of the Earth. So you can imagine the surface of the Earth being the surface. It's also the manifold, but if we, for the moment, just view this as the surface, then if you fix S0, you get geodesics. This would be the great circle. So this would be you and your friend both walking from the equator towards the North Pole along a great circle. And let me draw a little figure after writing one more sentence. The tangent vector or the tangent vectors to these geodesics are, we always denote them by TA, and these would be called dxa over d lambda for fixed s. And we define a second vector, and this second vector is n, a, and this vector we denote by dxa, ds for fixed lambda. I'll draw a picture in a minute, but if you go back to my initial example on the surface of the Earth, this vector n would be the vector, or would not quite, because the vector isn't part of the surface of the Earth, but you can think about the vector n as the vector that connects the two geodesics, and the tangent vectors ta, well, being the tangent vectors of the curve. So what we are trying to understand is the dynamical behavior of this vector that you can really think about as the connecting vector between two geodesics. Let me try to draw some nice picture here. Here's our surface. Then I use a separate color for those ones. My idea is have to flow. The lambda flow is up and the s flow is to the side. So here I have something like s1, s2, s3, s4, for instance. And these guys would be some tangent vectors ta here. So I'm just making this a bit dashed. Just as one. This would correspond to some lambda 1. Here we would have lambda 2, lambda 3. And the idea is that here you would have a second vector, NA. And what we're interested is, how does the vector n change as we move along those nearby, or if we move along the geodesic? And we'll just note that those blue lines, these are geodesic curves by assumption. So we say that for fixed S0, this is a geodesic. This is in additionally a finely parameterized, so we can always make that choice. However, I shall point out that we cannot also assume that these are geodesics. They're not. So these guys are not geodesics. What we eventually want to derive is a form of acceleration equation for this quantity n, something like n double dot. This is what we are after, because then we can think about something like Newton's second law of motion. If the distance between two objects changes over time, then there's probably a force acting between those points, and this is sort of the direction in which this is going. In order to get there, we need to do a couple of calculations. The first one we begin with is the following. So let us consider the following quantities. The first one, we differentiate xa twice, first with respect to lambda and then with respect to s, the other way around, s first, lambda second. Lambda first, s second. So dxa d lambda is the tangent vector, which means we have here ta, and because ta is not explicitly a function of s, the functional dependence comes through x, which itself is a function of lambda and s. We can write this as dx, sorry, dta dxi dxi. These should be partial derivatives. S, which we can write as now ni dta dxi, or in our other notation dita. If we look at the object and we change the order of differentiation, which should not affect the result, we get d over d lambda acting on na. By the same argument, we then get dna dxi dxi d lambda, which we can then write as ti dna dxi, or ti di na. These two must be the same. Hence we have ti partial I na is the same as ni partial I ta, which is also equivalent to ti nabla I. Na equals ni nabla I ta. To see this final part, if we write out again what the meaning is of the covariant derivative acting on a vector, partial I na plus gamma isa ns, and on the other side ni partial I ta plus gamma isa ts. All we have to look at is the Christoffel symbol component terms, and we recall that the Christoffel symbol in general relativity is symmetric in the lower two indices. Therefore, Ti ns with the gamma a is the same as ni ts with the gamma and an upper index a. which means we can just change this to blue, that those two terms cancel, and we have that. This is our first little intermediate result. How can we interpret this term? As I said, the vector n, you can think about this as the vector that connects two nearby geodesics. Nabla NA is something like the change of n, and because it is contracted with the tangent vector of the geodesic, we can simply interpret this as the rate of change of n along the geodesic. We can interpret Ti nabla I Na as the rate of change of Na along the geodesic. Because we can view this as one derivative, we can also interpret this as the relative velocity. We can also view this as the relative velocity between nearby geodesics. And while I haven't said this really explicitly, you should really imagine the distance between those different geodesics to be infinitesimal. Otherwise, arguments of this type wouldn't really work. So we are really considering infinitesimally nearby geodesics. If we make this interpretation, we can take this one step further. Therefore, the object Tj nabla j acting on Ti nabla I Na would correspond to the relative acceleration between nearby geodesics. And if we hear something like relative acceleration between nearby geodesics, you should be immediately thinking about Newton's laws, which tell you that a force is related to an acceleration, which means it is through this equation that we can somehow connect the concept of a gravitational force to some geometrical quantities, which will appear in this derivation. Let us see what we can say about this object and how we can write it differently. Tj nabla j Ti nabla I Na is the same as Tj nabla j ni partial I, oopsie, nabla I, Ta. This follows from this property here that we derived. By star. Next, the covariant derivative acts on two terms. Therefore, we can apply the product rule. This means we get Tj. I'm now using brackets to indicate this. So the covariant derivative hits the ni first. Nabla j ni. Nabla ita plus tj ni nabla j nabla I ta. Next, we use a nice little trick. We don't touch the first term. We just leave it alone for a second. Nabla j ni nabla ita. The question is, how can I force the Riemann curvature tensor into this? Well, I can recall that nabla j nabla ita minus nabla I nabla jta is minus the Riemann curvature tensor. Hence, I can swap those indices around. I j ta and then let me just write this. We use nabla j nabla I ta minus nabla I nabla j ta, which according to my conventions is minus r j I s a t s. So if I have this object here, which is that one, I can underline this to make it really crystal clear of what we are doing here. Then I can shuffle this bit to the right hand side, which is that term. So this minus sign becomes a plus, and then I have minus r j I a. Now I have to be slightly careful. S T S and here I have NI and TJ. So be careful with this so that it's not too confusing. Need another page. Let me just copy this down again so that I can see this in the next page. TJ nabla JNI nabla ITA plus TJ NI nabla I nabla JTA minus the Riemann curvature tensor term. TSTJNI. I now want to look only at the first two terms. First two terms. These two here. And what I want you to look at is the particular combinations here. So there's a tj out in front of everything. And we can also recall that tj, nabla j, and I can again be rewritten using star. So I have this term and I can rewrite it as that term. First two terms. I have tj nabla j ni nabla ita plus tj ni nabla I nabla jta. This is the same as nj nabla j ti by star again nabla ita plus tj ni nabla I nabla j ta. I'm now doing a little renaming here of indices. You see in this term the only free index is a, but we have summations over j and I. So I can rename j to I and I to j. nj nabla j ti nabla ita plus ti nabla j nabla j nabla ita. Remember that your summation indices can always be renamed to have the most convenient name available. And what we now see here is something like the product rule appearing. Namely, we can now say nj nabla j acting on ti nabla I ta. Let's have a look whether this is correct. So one of the terms would be nj nabla j ti times nabla ita. That's the first term. And the second term is njti nabla j nabla I acting on ta. Nabla j nabla I acting on ta. So this is correct by the product rule. Now comes something that you may not recall straight away. We assumed the S equals constant curves to be geodesics. We proved that geodesics satisfy precisely the equation Ti nabla Ita equals 0, which is exactly the thing here in the bracket. So see the previous lectures, see previous lectures. If I'm not mistaken, I called this theorem geodesic 2, because it is not the way we originally introduced the geodesic. Which means the two terms underlined in red are 0, which is why I did it in this particular way. Hence, we find, let's collect what we actually started with. We started Tj, so T nabla acting on n. T nabla acting on n. Because the first terms taken together vanish, we are left only with the third term. Minus Rji Sa. And we contract with Ts Tj Ni. That's correct. Now, only for the last result, we introduce the notation dNA over d lambda to mean Ti nabla I Na. Some of you will have seen a notation of this type. Sometimes this is called the material derivative. It is sometimes called the Lagrangian derivative in fluid mechanics, or it is sometimes also called the convective derivative, generally related in a fluid type situation, because we are interested in the derivative along a flow. Your flow here is given by the tangent vector of the geodesics. Most of you will have seen something like this before, obviously never in the context of differential geometry, but this kind of derivative along a flow is not a new concept. In this notation, we have that the second derivative of n along the flow, second material derivative, second convective derivative, or related to some form of acceleration, is minus Rji Sa Ts Tj, and all this is acting on Ni. And only to make the signs ever so slightly nicer, I'll swap the indices I and j over, which picks up another minus sign to compensate for this one, in which case I then get I, j, s, a, tj, ts. I can just swap them around. And all this is acting on n, which is the geodesic deviation equation. This is the final ingredient that we need before we are able to formulate the Einstein field equations, or more precisely, the final ingredient needed to connect quantities that have an origin in differential geometry to objects that have their origin in say Newtonian mechanics. So in particular, what I want you to see here is a form of acceleration between two nearby geodesics, and this is determined by the curvature of the space. So going back to the example that we started with in the lecture, if you and your friends are both standing at the equator some distance apart, then this separation would be characterized by the vector NA. As you're walking towards the North Pole, your direction of travel is determined by the tangent vectors, and this object here determines whether you are moving closer to each other, further away from each other, or whether the distance between you and your friend remains constant. So something that you can immediately see here, if the Riemann curvature tensor identically vanishes, the separation between two geodesics does never change, which is equivalent to the parallel postulate. So two parallels don't intersect. I mean, they do at infinity, but if we think about finite parallels, their distance remains in a sense constant. What you should also note here is something which gives us a little bit of a view of why maybe the Riemann tensor does not appear in gravitational field equations. You see, you are doing the contractions over indices 2 and 3, which is equivalent to the contractions over indices 2 and 4 with the minus sign, which shows you that it is more, or at least you can think about more of the Ricci tensor entering this equation than the full Riemann tensor because of this summation with the tangent vectors that is taking place. And this is precisely the kind of arguments that I'll put forward in order to motivate the Einstein field equation, and in order to link quantities that are well known in Newtonian mechanics and Newtonian gravity to objects which are genuinely geometrical. And this is all for today.